In this section, we're going to talk about circular functions. Circular functions are things like our trigonometric ratio functions, but set equal to y. So for example, y equals sine of x is one of the 6 circular functions, for example. And they're called circular functions because given the coordinates on the unit circle, we're going to be able to define each of the 6 circular functions. Then we'll be able to find their reflections against each of the axes and the origin. We're going to determine the 6 trigonometric function values for any real number input where the coordinates are the point on the unit circle to remember that real number are given. So we're going to, again, relate the unit circle to the function input-output pairing. And then we're going to find function values for any real number. So not just special angles, any angle. And we'll need to use a calculator for that. And we'll graph all of our 6 circular functions. So we've talked about the ratios, the sine of x, the cosine of x. We just haven't yet expressed them as a function in terms of y and graphed the x and y variables together on a 2-dimensional grid. We've just seen values on the unit circle. So, quick review. What do we know about the domain of the 6 trigonometric functions? If I look back a couple pages into one of the previous sections, we had made a chart for our special angles, here we go, our angles 30, 45, 60, as well as the axes, so 0, 90, 180, and 270. And we had said at this point that sine and cosine were always going to be defined. They were never undefined, but tan, cosecant, secant, and cotangent did have a few spaces, an axis or two, left and right of the same axis, where they were undefined. So we can talk about domain in terms of what we learned in that previous section. So as far as the domain of sine of x and cosine of x is going to be all real numbers. We can have any inputs. Those were never undefined. But the domain of the other 4, so tangent of x, cosecant of x, secant of x, and cotangent of x, is going to have domain exclusions. They're going to be values that are undefined. So they're all going to have domain exclusions. Domain exclusions mean values that x is not allowed to be. So x is not equal to, and the number does change depending on which of the functions you're looking at, so I'm not able to list it for all of them, but we'll talk about each of those coming up soon. Okay. On the unit circle where the radius is 1 unit, what is the relationship between the angle and the arc length swept out by the angle of that circle? Well, we know that the arc length is equal to r times theta, where theta is in radians. And if we are on the unit circle, in the unit circle, we know the radius is 1 unit on the unit circle. So this means that the arc length is equal to the angle on the unit circle. Since the r value is 1 times theta is theta. So on the unit circle, the angle is the arc length. Okay. So that's the important connection between s and theta here. So if we measure all of the angles from the positive x direction, so that's our direction that goes counterclockwise from the positive x-axis, then the point on the unit circle with coordinates x, y creates an arc length s equal to theta that defines the 6 trigonometric functions for that angle. Since s is equal to theta, we often will think about these in terms of theta as the input. The reason I'm not using x as the input is because x is a coordinate for the ordered pair in this diagram. The letter is going to be a symbol here for the arc length on the unit circle or the angle. So often I will see this one here written as sine of theta equals y instead of sine of s. I actually would prefer myself to use the theta in place of s because it's easier for me to tell that that's a distinct letter instead of an extra s on cosine, or it just looks a little weird to me to see the s input variable here. So you can imagine replacing each of these s's with a theta if you prefer that notation as well. But we do have the fact that they're equal because we're on the unit circle right here. Okay, so we have angles as our inputs for all of these. And then the output is, it says y. So if you keep this in mind, for our sine, we know that the x value and the y value, we know that sine opposite is y, divided by hypotenuse is 1, so y divided by 1 is y. So that should match our sine ratio for that angle, or for the arc length s. Same thing for cosine, adjacent over hypotenuse, that's x over 1, so we have x. And then similarly for tangent, secant, cosecant, and cotangent. One of the important notes I want to make right here is for these first two, since the sine of s is equal to y and the cosine of s is equal to x, we can rewrite our ordered pair, x comma y here, as the ordered pair cosine, I'm going to use the theta notation, comma sine. The cosine of the angle or arc length s, same thing in the unit circle here, is the x coordinate, and the sine of s is the y coordinate. So any ordered pair can be written in terms of the cosine of the angle, comma the sine of the angle. All right, any trigonometric function with a domain composed of real numbers is a circular function. They're circular functions, again, because they're based off of a definition that is all about the unit circle here. Also noting right here that the domain of these ones is all real numbers, as we mentioned up above. And the domain of these will have exclusions whenever the denominator of the ratio is 0. So for the tangent, whenever x would be equal to 0, that would be excluded from the domain. So it's defined as long as the x value is not 0. The y value would be equal to 0 here would cause this to be undefined. So the exclusion is as long as y is not equal to 0, this is defined, and so on. So I'm going to write a little bit more right here just to emphasize that these lines right here are part of our domain exclusions. We'll need to refine them, but that is the initial basis of the domain exclusions. When I say refine them, that's because right now they're in terms of an output value, and we want to refine them in a little bit to be in terms of the input value that would cause this to occur. Okay, so that's an initial look, though, at our domain exclusions. All right, so here is our unit circle, and the unit circle now has been filled in for all of our special angles. So we've got our special angle of 0 degrees or 360 degrees, corresponding with the radian measure of 0 radians or 2 pi radians. And we know that that is at the ordered pair 1, 0, so that's right there on the x-axis. So I'd be able to read these values, the 1 and the 0 right here, as the cosine of the angle, comma, the sine of the angle. So if I know the coordinates for one of my points, I do know the cosine and sine value at the angle. If I know the cosine value and sine value Don't forget, I can get the tangent value because we're going to recall that the tangent of an angle is equal to the sine of the angle divided by the cosine of the angle. So just by knowing these two, sine and cosine, I can get to all six. I can divide them to get to the tangent, and I can take their reciprocals to get to secant and cosecant. And if I can get to tangent, I can take its reciprocal and get to cotangent. So these ordered pairs are going to allow me to find all six trigonometric ratio values for the function, for all six functions. Okay, so we are going to need to work on memorizing the unit circle, but we want to be smart about it. We're going to use symmetry and patterns, and I'm just going to talk about those symmetry and patterns right here. So first things first is we'll talk about the axes. So we've got our x-axis, and on the x-axis, we'll know that, of course, we're at the point 1, 0 on the right-hand side. And then we'll be at the corresponding point negative 1, 0 on the left-hand side. And again, those two angles are going to be 180 in degrees or pi in radian measure. These have in common the fact that the x-coordinate is 1 or negative 1, and the y-coordinate for both of those is 0. So the cosine value is either 1 or negative 1, and for both of these angles, the sine value is going to be 0. Okay, then let's look at our y-axis. And on our y-axis, the ordered pairs on the unit circle will be at a height of 1 or negative 1. So we're at 0, 1 or 0, negative 1. We know that these in degree measure are the angles 90 degrees and 270 degrees. And those would correspond to the radian measures of pi halves and 3 pi halves. And so for those four special angles, 5 rotating back to 2 pi, 0 and 2 pi are the same angle. So 4 unique angles right here are all based on the fact that they lie on one of the axes. There's a bit of symmetry between left side, right side, and top side, bottom side. Same value, but opposite sign. So keep that in mind. All right, so I'm going to go ahead and now look at our 30, 45, and 60. I'm going to start with the 45s because there is a relationship between 30 and 60. So if I talk about 30, I want to talk about 60 as well. Let's just get our 45s done first. So for our 45s, they're the easiest of the non-axes values to remember because square root of 2 over 2 is the same x and y coordinate for the ordered pair. And that's going to be at our angles 45 in degrees, and that would be pi fourths in radians. Pi fourths because if that's pi, that's half of pi, and that's half of pi, so that's a quarter of pi. Okay. Now, if I know the ordered pairs for the pi fourths angle here, I'm going to talk in terms of radians, then I should, by symmetry, be able to figure out the ordered pairs for any of the other that have pi fourths as a reference angle. These are going to have the same values, but we're going to keep in mind that the x-coordinate is negative on the left-hand side. The y-coordinate is still positive up here. Down below, they're both going to be negative. And then on the quadrant 4 on the right-hand side down here, the x-coordinate is back to a positive value. We're on the positive x-axis, but the y-coordinate is negative. If this is 1 pi fourths, this would be 2 fourths or 1/2, which makes this angle here 3 pi fourths. 4 fourths is 1, which makes this angle 5 pi fourths. 6 fourths reduces to 3 halves, which makes this one 7 pi fourths. So we can count around the circle. If I know just this one quadrant, we're going to be able to see that by symmetry, I'm going to be able to count around to all of the other angles. Similarly, I could do this in terms of degrees, 45 degrees, 90 degrees, 90 plus 40 is 135. 90 plus 45, I meant to say, is 135. If I add 45 again, I'm at 180. If I add 45 to 180, I'm at 225. Plus 45 would be 270. plus 45 again is 315. So just by adding 45 all the way around, I can get all of these angles. Okay, now on to our 30 and 60. So for our 30-degree angle right here, adjusting my colors, we talked about for the 30-degree angle and for the 60-degree angle, how we knew that these were going to use the same two values, but that our 30-degree angle, remember, was the one that was longer, and our 60-degree angle was the one that was shorter and taller. So the longer angle is going to have the larger number first. So it's going to have the 3 square root of 3 over 2, comma the 1/2. And then the 60 is going to have the larger number second. The square root of 3 over 2 is in the y coordinate, since this is the taller triangle. And the smaller number is going to be first. So that helps me remember which order these two values need to be. So for 30 degrees, we're at root 3 over 2, 1/2. And at 60 degrees, we're 1/2 root 3 over 2. Okay, so 30 degrees, that's a measurement of pi sixth. And 60 degrees, that's a measurement of pi thirds. This is 1/6 of the circle. Note that pi thirds, that is 2/6. So I'm going to make a quick little note of this in a light color. So when I'm counting by 1/6, pi thirds is 2/6. So I have 1/6, 2/6, 3/6. 6 divided by 3 is 2, so 3/6. Then over here, I would have 4/6. And then finally over here is the unique one that doesn't reduce. That's my 5 pi sixths. So that's how I can determine where the partner to pi sixths is. 2, 3, and 4 pi sixths all reduce into something else, but 5 pi sixths doesn't reduce. So this is the same ordered pair as root 3 over 2, but of course we have a negative x coordinate. 5/6, so 6/6 is 1. 7/6 does not reduce, so that's the next one that's going to be identical to the pi sixth, but again with the negative x and y coordinates here. 7/6, this one here would be 8/6. 8 pi sixths does reduce, so that's going to reduce to a third. This one would be 9 pi sixths. This one would be 10 pi sixths, reduces to 5 pi thirds. And then the next one that doesn't reduce is 11 pi sixths. So that's the same values as our pi sixths, with again the negative y coordinate. Again, I'm trying really hard to demonstrate how if I know just the first quadrant, if you memorize just the first quadrant, you can count your way around and get all the rest. Okay, so we had our pi thirds. We have our 2 pi thirds here. 4/6 reduces to 2/3. Same values as pi thirds, but the negative x coordinate. 2/3. 3/3 would be the same thing as 1. Then we're down here at 4 pi thirds. That was from our 8 pi sixths. And again, same values, but both coordinates are negative. And then back over here, this one's going to be the one that reduces to 5 pi thirds. Still have the 1/2, but we have the negative with the square root of 3 over 2 because we're in the fourth quadrant. All right, so it's talking about those mostly in terms of radians. In degrees, it works the same way. 30 plus 30 is 60, plus 30 is 90, plus 30 is 120, plus 30 is 50, plus 30. You're going to add 30 all the way around. And again, all of the ones that correspond with a 30-degree reference angle are the ones, oops, I didn't green up this one, are the ones that we've now highlighted in green. Okay, I find it easier to do in radians. We can talk about whether they reduce or not. In terms of degrees, you just need to look at where they fall in your picture to know which ones match up with 30 versus the wider ones here, the taller ones, which match up with 60. Okay, so hopefully that helps you start to work on memorizing this pattern. Make sure you memorize the first quadrant. From there, you can develop all the rest. There's only really 3 things to memorize. You probably don't need to work on memorizing these because you know the coordinates on the unit circle here, 1, 0, 0, 1. You're going to know those. Memorizing this little part right here and then going around the circle will help. Right. So the next page right here, there is a blank unit circle. And so you're going to fill this in for yourself for practice. Make a note that this is broken into 12s just to make things equally spaced. You're not going to be using all of them. You're going to be using the markers that mark out as pi sixths. You're going to be using the markers that mark out as pi fourths. And you're going to be using the markers that mark out here as pi thirds. The only reason that these extra ones here, so we're not going to use the extra ones. The reason for having the extra ones is it makes it equally spaced for all of them because the common denominator between pi sixths, pi fourths, and pi thirds is 12, right? 3, 4, and 6 all divide into 12. So this is 1 pi 12th, but that's not a special angle. It just makes it so that we can draw a nice little picture right here that's evenly spaced. Just want you to know that you're not going to be using the pi 12ths markers when you fill this in. You're going to be using the 0, pi sixths, pi fourths, pi thirds, pi halves, and so on around the rest of the triangle. Fill it in with all of the angles and all of the ordered pairs for each of the special angles. So not these two, of course. So I'm just going to say we don't need those two. And then similarly, we won't need these two, and so on. We're going to do these and fill them in. Okay. So try not to look at the unit circle that you have already filled out. I try to do this for practice, and if you need extra copies, you can get extra copies of this on Canvas so that you can practice this, working on memorizing all of the ordered pairs and angles. Okay. On to the next page, topic 1, we're going to do some reflections on the unit circle. So on the unit circle here, for a point x comma y, we know that we have the cosine of an angle, comma, the sine of an angle. And in the first example, I want to determine any other possible coordinates for a point on the unit circle with a given coordinate. Okay. So, if the x value is 1/2, so I know this is 1, so 1/2 would hit up here. And it would hit down here as well. Okay, so on the unit circle, there are going to be two angles that have an output or a cosine value of 1/2. I want to know which of those two values, so cosine of the angle is going to be equal to 1/2. What are the two angles that make that happen? If I remember from my unit circle, this is the shorter, taller. So this is going to be the angle pi thirds. So one of my angles is pi thirds. And the other angle is, if that's 1 pi thirds, 2 pi thirds, 3 thirds is 1, 4 pi thirds. This one would have to be 5 pi thirds. Now, if I think about this in terms of a function, you might be looking at your circle and thinking about the vertical line test, but that's not actually what we're looking at here because this is just a representation of the point. What we're thinking about is that a single angle gives a single output, and that is true. So this is a function because the angle pi thirds has one and only one answer for its cosine. But there are lots of different angles that would give the same output. So it is a function, it's not a 1-to-1 function. So there are two answers to this. If we want to find the angles that give the that x coordinate. Okay. All right. Now, my goal right here, I haven't actually finished the goal. That was part of my goal. So determine any other possible coordinates for a point on the unit circle with a given coordinate and draw the sketch. So I actually need to list the coordinates since they were talking about those full coordinates here. So I found the angles, but let's talk about the ordered pair coordinates here. This one is 1/2, comma, square root of 3 over 2, knowing that that is the ordered pair that matches for the pi-thirds angle. And then this ordered pair here, of course, is 1/2 with negative square root of 3 over 2. So that's part of what we were asked right here as well, was find the coordinate points for that particular value. All right, so we're going to continue this. This is extra on this one. I'm not going to be able to find the angle exactly every time. I got excited about it because 1/2 was one of my special ratios. But I'm going to notice for 2/3, 2/3 is not in any of my ordered pairs on the unit circle. But I'm still going to be able to find out the coordinate pairs. So let's take a look. So we're going to draw ourselves a unit circle. So this circle has radius 1. And if the y value is negative 2/3, negative 3/3 would be 1, so negative 2/3 would be here. The angles would be approximately here and here. I don't know what they are. I'm not actually being asked to find what they are right here. I'm being asked to find what the coordinates for this ordered pair are. So I need to find the x value, and if I think about this as a triangle right here, I know that its radius is 1, that's the hypotenuse, because it is on the unit circle, and I know that the y value is negative 2/3, and so I'm going to be able to solve for the x coordinate. Pythagorean theorem, right? So I've got x squared plus negative 2/3 squared equals 1 squared. So x squared plus 4/9 is equal to 1. That means x squared is going to be equal to 1 minus 4/9 will give me 5/9. And I can do the square root of both sides, and I'll get plus and minus the square root of 5/9, or the square root of 5 over 3, since I know the square root of 9 is 3. All right, we were doing the square root of both sides here, and we get our plus and minus. Now we absolutely do need both the plus and the minus because we know that we're going to have a positive x coordinate on the right-hand side and a negative x coordinate on the left-hand side. So the two ordered pairs that we would have here would be, I'm going to write the left-hand side one first. That's going to be negative square root of 5 over 3, comma, negative 2/3. And then we also have positive square root of 5 over 3, comma, negative 2/3. So these are the two ordered pairs on the unit circle here that have a y coordinate of negative 2/3. Okay, so let's take a look at the last one. X is equal to negative 1. So again, on my unit circle, the only place that x is going to be exactly equal to negative 1 is going to be right here. So there's only one location, and that is going to have the ordered pair there, negative 1, comma 0. And that's going to be the only way for x to be equal to negative 1 itself. So I actually do know the angle for that one, like I was able to do over here. That is a special angle. So that's going to happen at an angle of pi. Okay. Now, I could find the angle for this one using an arc trig function. It's not required by this question, but I would definitely have to use a calculator for that one since these values are not on the unit circle. For the ones that are on the unit circle, I know the angle because I know when the trig ratio is equal to that particular value. I can see the angle there. Okay, so that was a bonus. We weren't asked to find the angle, but hey, we did know it, so we might as well write it down. All right, now we're going to continue and look at the angles a bit more. So our next goal is to determine the coordinates on the unit circle that defines the following angle. Draw a sketch showing the angle, the point, and the arc. Okay, so circle. So I know this would be the angle 0. I'm not listing the x coordinate, I'm listing the angle here. This would be the angle pi. This is half of pi. And so pi fourths is going to be a quarter of the full semicircle, therefore half of the first quadrant there. So that's the angle pi fourths. The angle we're going to mark here. So we've marked the angle. We're going to mark the point and the arc. So the arc itself is this portion, and we know that that is a distance of pi fourths since we're on the unit circle when the angle is pi fourths. Now, we might not always know the coordinates, but for this one, since it is a special ordered pair, because pi fourths is a special angle, I know the coordinates are positive square root of 2 over 2, comma positive square root of 2 over 2. So if I know the angle, I'm just going to go ahead and write it in. If I know the special angles coordinates based on the trig ratios. I'm not going to know the ordered pair for this one, but let's go ahead and make a drawing. Okay, so again, we're just starting with a circle, and on this circle, we'd have the angle 0. This would be the angle pi, and this would be the angle pi halves. Now, I know that pi is approximately 3.14. So pi halves is going to be approximately 1 point, I don't know what 3.14 divided by 2 is. So let me find a calculator. If I divide pi by 2, it's 1.6 something. So, close to 1.6. So it's approximately 1.57. The only reason for thinking about those in terms of decimals is that I need to figure out where 0.4 sits. And I can tell that it's nowhere near pi halves, so it's actually going to be quite small down here at an angle of 0.41152. So that's how big the angle is. And then the arc is a distance of that same measure up along the outside edge there. And the point would be this point right here, and its coordinates would be whatever the cosine of 0.41152 are, comma, the sine of 0.41152. Now, I don't know what those values are, but I can get them if I'm interested. So I'm going to clear my calculator. I'm going to make sure that it's in radian measure, which is the default. So it is in radian measure. Again, I'm not specifically asked to do this, but why not? Let's find the coordinates for this point exactly. So this would be the point that had 0.9165 for its x coordinate and had 0.4 for its x coordinate and 0.411 or 0.400. We'll just go with 0.4 there for its y coordinate. So again, on the x coordinate, that's where 1 is, and 1 for y is up here. So we are pretty close to 1 on the x-coordinate, and again, less than half. That does look like less than half if that's where 0.5 would be. So our diagram's actually pretty good. Pretty happy with the way that diagram turned out. 0.4 for the y-coordinate is less than where 0.5 or 1/2 of that ratio from 0 to 1 would be. Perfect. Okay. All right. So that would be the ordered pair for this point right here. We'll just not write it up there. There's just not a lot of space. So that's the angle. This is the point. Okay. So we've got ourselves the angle. We've got ourselves the ordered pair, and we've drawn it. All right. Once again, we are going to draw a unit circle. This is for the angle now pi. So on the angles, that's my angle 0. This is my angle pi. And so the angle is from 0 to pi. The arc is tracing the unit circle all the way from 0 to pi. And the point, I know that point, is at -1, 0. It's at -1 on the x-axis, 0 on the y-axis. Okay. All right. So next. Oh, there's more on the bottom. Continuing. Number 3 says the following points are on the unit circle. Find the coordinates of their reflections across the x-axis, the y-axis, and the origin. Okay. So again, that's supposed to be a circle. This point on the circle has x-coordinate 3/4. So let me separate this into fourths. -3/4. And y-coordinate square root of 7/4. So this is the ordered pair -3/4, square root of 7/4 on the unit circle. Okay. So we want to find the reflection across the x-axis, the reflection across the y-axis, and the reflection across the origin. So I'm just color coding these so that it's easy to tell which one we've done. So if I reflect across the x-axis, that would be this point right here. So when I reflect across the x-axis, the x-coordinate's going to stay the same, -3/4, the y-coordinate's negative in this quadrant as well, so negative square root of 7/4. So this would be our point reflected across the x-axis. If I reflect across the y-axis, it's going to be over here. Again, my circle is a little fat on that side, so it looks maybe a little longer. It should be exactly the same if I was able to draw a perfect circle. And so the x-coordinate is positive in quadrant 1. So this will be the point +3/4, positive square root of 7/4. That's going to be our reflection across the y-axis. And if I reflect across the origin, that should be the same thing as reflecting across both the x and y axes. And that is going to have a positive x coordinate and a negative y coordinate. So this is our point reflected across the origin. Right. One of the reasons for thinking about the potential symmetries across the x-axis, y-axis, and origin is that all of these angles have all of these arcs, these lines, have the same reference angle. So the angle will be in relation to itself. Same reference angle. So I'd be able to take that angle and either subtract or add to pi, or subtract or add to 0 or 2 pi, in order to find the angle if I knew just one of them. So that's just an idea of what I might do if I had to find the angles of something that was symmetric to a known angle. All right, so right now we're just looking at those coordinates. So let's go ahead and look at the next one here. Let's try to draw a circle. It's a pretty good circle, I think. I've got myself a circle, and the original point is at negative square root of 3 over 2, negative 1/2. So that's going to be negative root 3 over 2, negative 1/2, about here. This point has to have a larger x value and a shorter y value. So the angle is going to be closer to the x-axis than it is to the y-axis. I'm just trying to draw this somewhat accurately here. So this is the point negative root 3 over 2, negative 1/2. And I want to reflect this across the x-axis. So across the x-axis, my reflection is now going to be up in quadrant 2. This is my x-axis reflection. And the x-coordinate is still negative, square root of 3 over 2, but the y-coordinate would be positive 1/2. So this will be our x-axis reflection. The y-axis reflection is going to put us in quadrant 4 down here. And the x-coordinate is going to be positive, square root of 3 over 2, but the y-coordinate is still negative 1/2. That's our point reflected across the y-axis. And when we reflect that original point across the origin, it reflects it across both x and y. So right here, this point should be positive square root of 3 over 2, comma, positive 1/2. And that is symmetric across the origin. Unlike the previous one, I do recognize this as a perfect, or a special value, I should say, as one of my special angles. And this is for the special angle pi sixths. So I could write in the angles for these. It's not asked in this question, but we know them, so why don't we go ahead and do this? Pi sixths, 2 sixths, 3 sixths, 4 sixths, 5 sixths. These are just the ones that don't reduce, right? 6, this is 7 pi sixths. 8, 9, 10, this will be 11 pi sixths. So I do happen to know those angles based on the fact that I recognize these as values from the unit circle. So again, knowing about the special values will help me with symmetry to draw the diagram that's going to have all of these angles have a reference angle of pi sixths. And you should be able to see that if you take pi and you subtract pi 6 or add pi 6, that does get you to 5 pi 6 and 7 pi 6. Same thing, 0 plus pi 6 or 2 pi minus pi 6 gives us that symmetry. They all have a reference angle of pi 6 away from the x-axis. All right. Topic 2, we're going to find some function values. So we know that we can use symmetry to find locations for any point in the unit circle, which also means we can find the trigonometric function values for their equivalent angles, as we were noting on the previous page. So we want to find trigonometric function values for each of the following using coordinates on the unit circle. So we're going to remember once again that coordinates on the unit circle are of the form cosine of theta, comma, sine of theta. The cosine value is the x-coordinate and the sine value is the y-coordinate. So if I wanted to find the sine of pi, I like to picture my unit circle and where the angle pi is. And if I know where the angle pi is, I know that that is at the ordered pair, -1, 0. And so the sine of pi is going to be equal to the y-coordinate, which is 0. So sine of pi is equal to 0. Okay. Cosecant of 3 pi over 4. So again, you can look at your unit circle, or you can draw yourself a unit circle here. I've got 1 pi over 4, 2 pi over 4, 3 pi over 4. This is the angle, 3 pi over 4. And I know that the coordinates, since this is going to have a relationship with pi fourths, are going to be root 2 over 2, root 2 over 2. But based on the fact that I'm in quadrant 2, the x-coordinate is negative. So negative root 2 over 2, comma, positive root 2 over 2. So you can look that up on your unit circle, or once you've memorized it, you're going to be able to fill that in for yourself here. Now, I don't want the sine or the cosine value. I want the cosecant value. So I'm going to note that this is the reciprocal of the sine value. So the sine value here is positive root 2 over 2. So the cosecant value is going to be 2 over root 2. And then we will rationalize this because it's one of our special ratios. So we'll multiply top and bottom by root 2. And that would give us 2 root 2 over 2. Square root of 2 times square root of 2 is 2. And those reduce. So this gives us root 2. Now, I personally don't memorize the values for cosecant, secant, tangent, cotangent. I derive them from sine and cosine. If you did have it memorized, that's fine. We can know that for a 3 pi fourths, which is got a reference angle of pi fourths, that's 45 degrees. The cosecant value is going to be square root of 2. So if you have it memorized, that's fine. And you could have went right to square root of 2. I personally don't take the time to memorize all 6 of them. Once I know the sine and cosine, those are the ones I memorize. I derive from there. So up to you. All right, continuing on, we're going to use the same kind of idea with tangent. So tangent, this angle is negative pi fourths. So that is pi fourths in the negative direction. So similar to the positive pi fourths, which would be root 2 over 2, this ordered pair is going to have a positive x coordinate with a negative y coordinate, so negative root 2 over 2. And if I want the tangent of negative pi fourths, I'm going to remember that tangent is equal to sine divided by cosine. It's one of our identities for tangent. And so I know the sine value is the y-coordinate, negative root 2 over 2, divided by the x-coordinate, which is positive root 2 over 2. And so it comes out as negative 1. Okay, I need the secant of pi halves. This is the angle pi halves. At that angle, the ordered pair would be 0, 1. I know that the secant is the reciprocal of cosine. This is 1 over the cosine of pi halves. And the cosine of pi halves is the x-coordinate, which is 0. So that's 1 over 0, which means the secant of pi halves is undefined. Let's look at the next one. The cosine of 10 pi. So we know that the angle over here is 0, or 2 pi, or 4 pi, or 6 pi. You can go around and around and around, right? 2, 4, 6, 8, 10. So 8 pi or 10 pi. So this is the angle that we're looking at. Its coordinates are 1, 0. So if I want the cosine of 10 pi, the x-coordinate here is 1. And the cotangent of 5 pi over 2. All right, so this is pi over 2. This is pi. This one would be 3 pi over 2. This is 0 or 2 pi. So 1, 2, 3, 4 over 2. This one is back to 5 pi over 2. So the angle for 5 pi over 2 will go around and back to here again. So it's the same angle as pi halves. So our ordered pair up there is 0, 1. And if I want the cotangent, tangent is equal to sine over cosine. Therefore, cotangent is equal to cosine over sine, reciprocal of tangent. So the cosine value, which would be 0, over the sine value, which would be 1, 0 over 1 is equal to 0. All right. Just as with degrees before, we can find the value of any trigonometric function for any angle using our calculators, provided that it's set in the proper mode. So make sure you always check your mode. If you're using degrees or radians, we want to make sure we're in the proper mode. So the ones above, I didn't need to use the calculator for because they were all special angles. Down below, sine of the angle 11.7, that is not a special angle. 216, that's in radians. That is not a special angle. 7 pi, though, is a special angle. So we'll talk about doing that one by hand and on the calculator. But these two right here are definitely not special angles. So going to my calculator, I'm just going to verify that it's still in radian measure. It is in radian measure. These measures are in radians. There's no degree symbol, so it's definitely a radian measure here. And I need to find the sine of 11.7 radians. So the sine of 11.7 radians is equal to about negative 0.76 198. So 20 if I'm going to use 4 places. So if I think about where that angle would be, I just want to make sure a negative value makes sense for this. So this is pi, it's about 3. This is 2 pi, that's 6 and some change. So this would be 3 pi. 3 pi is 9.4. This is pi, 3 pi over 2. So let's see. 1, 2, 3, 4, 5, 6, 7. So this is 3 pi over 2 or 7 pi over 2. And then this would be, again, let's see, 3 pi, 4 pi. I wanted to figure out what quadrant this angle was supposed to be in. So 4 pi is 12.5 and 7 pi, oops, new line there, 7 pi over, I thought I hit enter. 7 pi over 2 is 10.9. So it is an angle that is somewhere here where the angle would have went around and back to it. So this is where the angle 11.7 is. So on the unit circle, that angle would have a y coordinate that is negative. So just a verification, when you get a value right here, does that seem to be in the ballpark? Should have a negative y value? Absolutely. Negative y value of negative 0.762 sounds reasonable. Okay. We're not going to do that for this one because the angle 11.7 spun around twice. Can you imagine how many times we're going to spin around for 2016 as an angle? But just checking one of them helps us see how that would be done. So cosine of the angle 2016 radians would give us 0.6197 as the cosine value. I don't know where that angle is, but it must land in either quadrants 1 or 4 because the cosine value is a positive. That would be a lot of spins around. It's going to be really big to find, so we'll leave that one alone. All right, so in the next one, I'm going to find it in the calculator before talking about it by hand. So this is the cosine, or the cotangent of 7 pi, and it came out as undefined. So just a quick check at why. So our cotangent, we know that this is where pi is, this is where 2 pi is, so this will also be where 3 pi, 5 pi, and 7 pi are, any odd multiple of pi. So we're ending at a point like this, where the x-coordinate is -1 and the y-coordinate is 0. And the cotangent of 7 pi, tan is sine over cosine, so cotangent is cosine over sine. So cosine of 7 pi over sine of 7 pi. The cosine value is -1 over the sine value is 0. So as you can see, that should come out as undefined, and I can do this either with the calculator or by hand with my unit circle. Okay, so I'm going to shrink decimals for a little bit, and we're ready now to graph some of our trigonometric functions. Since we can think of sine and cosine as functions, that means we can graph them. These functions are often referred to as periodic functions because they repeat the same pattern over and over. We can see this on the unit circle. We get the same values over and over again, but we can also see it when we graph them alone. So this here is the graph of y equals sine of s. Remember, s is just the symbol for arc length or the angle when you're on the unit circle there. Okay. So the only the y coordinates from the unit circle have been graphed. So just a quick look at why these values make sense. We're going to relate it to a unit circle here. I'm only going to do this for the sine graph. So on the sine graph, we have the point, let's see, this is 1, 0, and this would be for the angle 0. Then we have the angle 3 pi over 2. Oh, sorry, that's 1 pi over 2. 1 pi over 2, which should be 0, 1. And let's do square root of 2 over 2, square root of 2 over 2 for pi fourths, and then just -1, 0 for pi. Can't do too many, it's just a tiny circle. Get your unit circle out to see more. So these are the angles on the x-axis. So at an angle of 0, the sine value is just the y-coordinate. So we're looking at just the y-coordinates for the sine value from the unit circle. So at an angle of 0, the y-coordinate is 0. At an angle of pi fourths, the y-coordinate is square root of 2 over 2, which is 0.707. That's about correct up here. At an angle of pi halves, the sine value is 1. Okay? And then coming back down to an angle of pi, we have a sine value of 0. So you can see how this curve was formed right here. And of course, back over to 2 pi, we're going to get back to 0. And at the angle 3 pi over 2 here, this is the ordered pair 0, -1. So the y value is -1. Okay? So 2 pi giving us back to 0 since 0 is the same angle as 2 pi. So it's a periodic function because it's going to repeat. This is one period of the graph. And if you were to see this graph continue on, you would expect it to do the same shape, right? It would start over, go up to 1, back to 0, and repeated cycle. That's what one period looks like. So that's where this graph comes from. This is the graph of sine of x. The domain of sine of x is going to be all real numbers. You can plug any angle in, so negative infinity to infinity, or all real numbers. And then the range of sine of x. So the domain is all real numbers. The range, notice that the highest y value we would ever get to is 1, and the lowest y value that we would ever get to is -1. So the range is going to be the interval from -1 to 1. It's because we're on a unit circle, and the highest the y coordinate can be is 1, and the lowest is -1. In between, it's in between those values. What kind of symmetry does the graph of sine of x have? So remember our symmetry discussion from earlier in the semester. This is symmetry across the origin. So it's symmetric with respect to the origin. So it has origin symmetry. And if you remember from earlier in the semester, this also means that it is an odd function. Odd functions were symmetric with respect to the origin. Okay, so let's now look at the cosine function. We could make a similar diagram and talk about the values for the cosine function. I'll let you do that. So I'm just going to look at the graph of the cosine function. One period of the graph of the cosine function will start at 0 and go to 2 pi. After 2 pi, you would imagine this graph continuing and repeating the pattern. So it also repeats the negative side there, of course. So this is our function here. Y is equal to the cosine of s, where that s value, that arc length, is equal to our angle when we're on the unit circle. The domain of cosine is again going to be -infinity to infinity, or all real numbers. It's just two ways to express the same idea. So all real numbers. And once again, the range of cosine, it's going to have a maximum height of 1. The 1 label got covered up by the graph, it looks like. And it's going to have a minimum height down here of -1. So minimum -1 to, again, maximum of 1 for our domain and our range. As far as symmetry for this graph is symmetric across the y-axis. So it's symmetric with respect to the y-axis. And if you remember from earlier in the course, this meant that we have an even function. None of these should be symmetric with respect to the x-axis, because then they would not be functions. Again, remember that from earlier. The only two types that are functions are going to be symmetric with respect to the origin or with respect to the y-axis. This is symmetric on both sides of the y-axis, so that function is even. Okay, continuing some more details over here. Now notice how both functions have regularly repeating maximum and minimum values. So this here is the graph of sine of x, and this one is the graph of cosine of x. We're talking about those maximum and minimum values. So we've got those repeating maximum, minimum values. So the maximum value is the same in a whole bunch of places. The maximum value, it occurs multiple times, and the same thing for the minimum value. It's going to have lots of places where it reaches its minimum value of -1, as long as you continue this graph further and further across the x-axis. Okay. Other features of this graph are that it has an amplitude of 1. and they both have an amplitude of 1. So amplitude is the distance from the center line, either up or down. So if you imagine where that center line is, if you count how far up or down, it's a measure of 1. So if you count from a peak to a bottom, that's twice the amplitude. That would be a distance of 2, 1 up, 1 down. The amplitude for these functions is 1. The other measure is going to be the period. That's the amount of time it takes for the function to repeat. So the period for both sine and cosine is going to be 2 pi. Every 2 pi, that function repeats. So here it goes from 0 up to 1, down to -1, then back up to 1. It's going to repeat again, going up to 1 next. Here it starts at 1, down to 0, down to -1, up to 0, up to 1 again, and then it's going to start going back down. That's what the period is, the amount of space it takes for a function to repeat. Okay. Consider any real number s and its opposite, -s. These numbers correspond to arc lengths in a unit circle that are symmetric with respect to the x-axis. So we've got the angle s here and -s. So that corresponds with the arc length s or -s. And in these two, again, the picture is the same thing. We're just thinking about the sine in one of them and the cosine in one of them. So if I'm thinking about the sine of s versus the sine of -s, for these two coordinates, the sine is the y value, so it's positive for s, and it is negative for -s. So we know that the sine of a negative input, we're calling the angle for the input x here, not the same as the x coordinate. So the angle is going to be negative. If the angle is negative, the output is going to be the opposite of what it would be if the angle was positive. So if sine of x would be equal to y, and sine of negative x would be equal to negative y. So sine of negative x is equal to negative of sine of x, right? It's the opposite. One is positive, the other is negative. So it needs to be the negative of the one that's positive. Okay, that is another way of saying that the function is odd. We already said that the sine function was odd. Remember the definition for odd was that f of -x is equal to negative f of x. So again, we're just seeing that principle of odd functions right here with the sine of x function. Okay, for the cosine function, we've got the cosine of x and cosine of -x. Notice that cosine is equal to the x value, and the x value is positive for both of these. Well, technically it's negative for both of these, but it's the same thing for both of these. They don't switch signs, right? The x value is the same value, whether it's 2 negative values or 2 positive values. If I was in these two quadrants, it's the same. So the cosine of an angle that is negative is going to be the same thing as the cosine value of the angle that is positive. That is a property of even functions that we saw very early in the semester, that f of -x is going to be equal to f of x. And that is also true for our cosine function graph. You have the same x coordinate for the positive angle and for the negative angle. Two negatives or two positive, but they're the same value. If they are two negatives, I'm not writing the negative coefficients because they divide off, right? Okay, and the bottom says, just as with sine and cosine, we can graph the remaining 4 trigonometric functions. However, we need to consider their domains first. So let's take a look at the tangent function. This is my graph of y equals tangent of s, where again, that input s is the angle. And if I look at the tangent function I can see that there are a lot of asymptotes. So there's going to be a vertical asymptote at negative pi halves. There's a vertical asymptote at pi halves. And there's a vertical asymptote at 3 pi halves. So that seems to be all odd multiples of pi halves. So all odd multiples of pi halves. So 1 pi halves, 3 pi halves, negative 1 pi halves, negative 3 pi halves, 5 pi halves. I expect there to be another asymptote and so on. So in order to write that short, I need to figure out how to express a number that is odd. So let me write up on the top of my page. If I want a number that is even, I can take 2 times any whole number. So k is going to be a whole number. It's an integer. It can be positive or negative. So if k is an integer, 2 times any integer is going to be even. So if I want to make an odd number, I can take any integer and I can add 1 to it. So that's going to be the way that we're going to express numbers that are odd versus numbers that are even. Okay, anything that's even, add 1 to it, you get an odd, or you can subtract 1, doesn't matter. Add 1, subtract 1, same difference, because k is an arbitrary integer. So I'm going to have vertical asymptotes whenever x is equal to an odd multiple of pi halves. So we're going to say 2k plus 1 for odd times pi halves. So that's going to be my vertical asymptotes. We use the 2k plus 1 to express the idea of odd multiples of pi halves. Okay, interesting. All right, so we're going to continue now. We got to look at the domain. If we have asymptotes when x is equal to an odd multiple of pi halves, the domain is going to be all x such that x is not equal to those odd multiples of pi halves. Those are the things that are not in the domain. So we definitely have that relationship between vertical asymptotes and domain. We're equal. In the asymptote, we are not allowed to equal for the domain. Now for the range. Y values, this goes down forever, goes up, goes through 0, goes up forever. Any of these goes through any y value, so our range is certainly going to include all y values, negative infinity to infinity. And then the period. The period is the amount of space it takes for the function to repeat. And so if I look at one of these little pieces of the function right here, any one of these is already repeating on this side. So this is going to be 1 period. And if it goes from negative pi halves to pi halves, that is a distance of pi, right? So if I take pi halves minus negative pi halves, that would add up to 2 pi halves, or pi. The period is pi. It's 1 pi. You can also think about this as, if you want to start at 0 just to make it easier to count, you can go from 0 to pi before you repeat. So it's just another way of seeing period. I think it's easier for myself to look in between these two and then just subtract. That's a distance of pi, but you can also see it on this side. It's a distance of pi for the period. That is different from sine and cosine, which took until 2 pi to repeat. Tan takes just until pi. Okay. After looking at tangent, we're going to look at cotangent, since tangent and cotangent are going to have very similar properties. So this is what cotangent looks like. It looks a lot like tangent, but it is the reciprocal. So it does have some differences. In the reciprocal, notice that any place that the tangent function was 0, the cotangent function is going to be undefined, because you're going to have that 1 over 0. And vice versa, any place that you were undefined in your tangent function is going to be a place where you're 0 in your cotangent function, because it's the reciprocal. So the asymptotes now are going to occur at 0, at pi, and at 2 pi. Those are our asymptotes. That seems to be all multiples of pi, not just the evens, not just the odds. So 0, 1 pi, 2 pi, 3 pi. So we're going to say it's at all multiples of pi. That's how I would say in words, but of course we do need to write equations. So x is going to be equal to k pi. Again, remember that k stands for any integer, right? So k is any integer. And if you don't write that, that is assumed. K stands for any integer. The shorthand way to write k as any integer is to say k is an element of the set of integers. We use a z for integers. I guess, is for imaginary numbers. You can't use that for integers, but it's z. I don't know why that letter got chosen, but it is the standard letter for integers. But that's doesn't need to be written every time. Just if you look in your textbooks, you might find that statement. We're going to assume that when I write a k like that, it's always an integer, so positive or negative whole number. Okay. Once again, there is going to be a relationship between the vertical asymptotes and the domain. If you have asymptotes at any integer, then any integer multiple of pi, then those are not in the domain. So the domain is x is not equal to k pi. The range, we go all the way to negative infinity and infinity on every little slice right here. So we're going to have all real numbers for the range. And the period, once again, we have everything happening within one set of asymptotes, and then it repeats. So it's going to be from 0 to pi for the period. So the period is pi, same thing that it was in the case of tangent above. All right, we've seen sine, cosine, tangent, and cotangent. So next we're going to see cosecant and secant. One of the best ways to look at the graph of cosecant is to consider what the graph of sine looks like. So this is the graph of the sine function that we saw previously. We remember that the cosecant function here is the reciprocal of sine. So anywhere that sine is 1, it's going to be 1 over 1, which is still 1. And anywhere that sine is negative 1, it's going to be negative 1 over 1, which is still negative 1. So these graphs are going to meet anytime the sine function was 1 or negative 1. Also, anytime the sine function would have been 0, you're going to have 1 divided by 0, so you're going to have asymptotes. So these asymptotes are going to come when the sine function is 0. The sine function is 0, we're going to get an asymptote, we're going to get an asymptote. For any other value, the smaller the sign, the higher 1 divided by that little tiny fraction. So we have these arcs that go up to infinity. They look a little bit like little bitty parabolas, but we know parabolas don't have asymptotes, so it is a different kind of shape right here. But this is going to be the graph of the cosecant function. Okay, so this one has vertical asymptotes. We've got one here at 0, we've got one here at pi, we've got one here at 2 pi. So that seems to be at all multiples of pi. So that's going to be where x is equal to k pi. There are some overlaps. This is the same thing that we said for our cotangent function. We are going to see some similar properties. This means that our domain is going to be x is not allowed to equal k pi. Again, domain and asymptotes occur in the same location, just one is allowed to equal for the asymptote and not allowed to equal for the domain. Now for the range. Okay, if I look at this function, the lowest it is allowed to equal right here is -1, and then it goes up to infinity. Then it is allowed later on to equal -1, and then it goes down to negative infinity. But nowhere is the graph of cosecant in between -1 and 1. It's not in that space at all. The sine function's in that space, but the cosecant function is not in that space, right? So the cosecant function is strictly above 1 and below -1. So for the range, we're going to be allowed to have anything that goes from negative infinity up to -1. Take a break. And then we're going to have anything that goes from 1 up to infinity. That's going to be the range of the cosecant function. The period, the amount of time it takes to repeat. So if I'm looking at this u and this u, the next u would be up here. So the period is going to be a span from 0 to 2 pi, or from -pi to pi, which again, if I subtract that, gives me 2 pi. So it is 2 pi for a period. Okay, so our last function down here, we're going to take a look at the secant function. In order to figure out what the secant function looks like, we want to look at the cosine function because secant is the reciprocal of cosine. So we've already seen cosine. I'm just going to take a look at this function here. Anywhere that cosine was equal to 1, the secant is still equal to 1 or -1, similar to what we saw with our sine and our cosecant. And anywhere the cosine function is equal to 0, that's where we're going to have our asymptotes. Okay, so the secant function is this function here. It makes these U-type shapes. They're in a different location than the cosecant ones above, but very similar properties for these graphs. Let's talk about where our asymptotes are. There is an asymptote at -pi halves. There's an asymptote at pi halves. There's an asymptote at 3 pi halves. So that seems to be, again, just the odd multiples of pi halves. 1, 3, 5, not 2 pi halves, which would be pi. There's not an asymptote at pi, so I've got to make sure I say just the odd ones. If I said k pi halves, pi is one of those because 2 pi halves reduces to pi. So just odd multiples. So odd, that is again a 2k plus 1. Make an even, add 1, it's an odd. Multiples of pi halves. Those are going to be vertical asymptotes. And those are going to correspond with our domain, which will be x is not equal to the 2k plus 1 multiples of pi halves, odd multiples of pi halves. Range, very similar argument to cosecant above. We get all these negatives up to -1. We don't have anything in between -1 and +1. So the range is going to be the same. It's going to be from negative infinity up to -1. And then it's going to start again at 1 and go up to infinity. The period, it's going to be 2 pi again. I can see that if I look from 0 to 2 pi, here at 2 pi is when it would start to repeat. So it's 0 to 2 pi. Or I can see the 2 u's here from -pi halves to 3 pi halves. And if I subtract 3 pi halves minus pi halves is 4 pi halves. 4 divided by 2 does reduce to 2 pi. So the period is, once again, 2 pi.